Okay, so here's the solution to the test. So we have this object moving at 3 meters per second, slides along the surface, flat surface, until it stops. So if you look at the object, you've got the weight putting down, you've got the friction force going to the left, you've got the normal force going up. So if you put all those forces together in our free body diagram, you've got F sub F going to the left with positive X going to the right. So when you put together Newton's second law, it's negative F sub F because it's in the negative X direction. Now the friction force is equal to the coefficient of friction times the normal force. The Y component of the force is, there's two. There's the normal force and there's the weight. So Newton's second law says that the normal force equals the weight. And the weight is the mass times the acceleration due to gravity. So it's 9.8 newtons. So the friction force is going to be 9.8 newtons times the friction coefficient, which is 1.47 newtons, which is positive. But the friction force, we've got a negative here, so the negative sign makes the acceleration negative, meaning the acceleration is from right to left, which is going to cause this thing to slow down. So now that you have the acceleration, you can use the constant velocity, constant acceleration equations given these three conditions: initial velocity, final velocity, acceleration. And if you use the fourth equation solved for delta x, you can get delta x is 3.1 meters. And if you use the second equation to solve for t, you'll get that the time is 2.1 seconds. Okay, the second problem is this thing sliding down the ramp has an initial velocity of 4 meters per second. Now, I ended up telling you to choose x positive going down. I solved it x positive going up. You get the same answer. And you'll see why it's probably better to do it down instead of up. If it's sliding up, pointing upwards probably makes the most sense. If it's going to slide down, you probably want to do it the other way. But let me just show you how this works. So you've got your free body diagram. We've got four forces. We've got the Y component of the weight, the normal force, which are equal to each other from Newton's second law. In the X direction, we have the X component of the weight and the friction force going in opposite directions. So the X component of the weight wants to pull it down. The friction force wants to slow it down, go in the other direction. So if you look at Newton's second law in the X direction is defined, notice these are, some people wanted to draw these vertically and horizontally, but they're always aligned with the inclined surface. So based on my positive X going up, the friction force is positive because it's pointing in the positive X direction. W sub X is pointing in the negative X direction, so that's why it's negative. The Y direction equation comes down to that the normal force is equal to the Y component of weight, which up here the Y component is W times the cosine of theta, 96.5. So that's the normal force. With the normal force and the coefficient of friction, you can calculate the friction force, which is 19.3 newtons. So that is positive. The weight, you subtract that. X component of the weight is W times the sine of theta. So you end up with a positive 0.23 meters per second squared. If I had defined the coordinate system the other direction, I'd end up with a negative. Now here's the tricky part. If you use the way that I did it, the velocities actually are negative. So you have a positive acceleration up the ramp, but the initial velocity is down the ramp, so it's going in the negative X direction. And it's continuing to go in the negative X direction. So for my coordinate system, the velocities are negative. If you did it the way that I suggested, the acceleration would be negative, but the velocities would be positive. So you use the fourth equation, solve for delta x. And with my coordinate system, delta x is negative because it's going down the ramp, which is opposite the positively defined x. If you had x positive down the ramp, then this delta x would be positive. Likewise, the velocities here are negative with a positive acceleration. Give you a positive time. If you had it the other way around, the acceleration would be negative and these would be positive, and so everything would have different signs and it would still be positive. So the time still comes out as positive. Again, you should never have a negative time. If you do that, then you've done something wrong. So these are the two answers. 33 meters down, took 13 seconds. Okay, next one, I kind of laid this out for you in class. The sum of the forces in the x direction are the components in the x direction, and if you use the angles defined relative to the positive x-axis, which are 35, 132, and 270, the signs all work out perfectly. The cosine of 270 is 0, so that term's going to drop out. So you just have this term and that term. The cosine of 122 is negative 0.530. Now what I did is I gave you T2. So this first equation here, if I plug T2 in, the only unknown is T3. So that's right down here. So I just plugged in 650 for T2. Solve for T3. I got 1,004 newtons. Then I can use that 1,004 newtons for in the second equation, plus the fact I was given T2. So you can see it here plugged in. Solve for T1, you get 1,225 newtons. And then to find the weight or the mass, the tension, because it's in equilibrium, the tension in the rope 1 is the same as the weight hanging, and then the mass of the weight is the weight divided by the acceleration due to gravity. So you get 125 kilograms. The third problem is frictionless, so we don't have to worry about friction. Again, I defined x positive going up. In this case, it makes more sense because I'm pulling this mass up the ramp, and this mass is falling. So first thing I did is I found the weight of object 1, mass times acceleration due to gravity, positive. Weight should always be positive. Then you have the x and y components. The x component is the weight times the sine of the angle. The y component is the weight times the cosine of the angle. So those are the two components. 80, w sub x is 80, w sub y is 123. Now, on this sliding mass going this direction, I've got two forces in the y direction. The normal force and the y component of the weight. Those are equal to each other because there's no acceleration in the y direction. So that's represented by this equation down here, the sum of the forces in the y direction. But it does accelerate in the x direction. So I've got m1 a sub x1. I've got the tension pulling in the positive x direction. I've got the x component of the weight pulling in the negative x direction. So that's my x equation for object 1. For object 2, this thing just goes up and down. So if you do Newton's second law there, you'll have m2 a sub y2 is equal to t minus w2. I define positive y going up. So t is up, so it's positive. w2 is down, so it's negative. w2 is just the mass times acceleration due to gravity. So I know w2, I know m2. Now, because of the way that I define my coordinate systems, you have that a sub x1 is equal to negative a sub y2. Because when this goes in the positive direction, this goes in the negative y direction. So you get this negative sign. And I just call this a, which is equal to a sub x1 is equal to a, which is equal to negative a sub y2. So in this equation, instead of having a sub x1, I put in a. m1 is 15, T is the tension, W sub x1 is 80. So that's the equation from the sliding mass. Then the hanging mass, I get the negative because of this relationship here. So I get negative 23 kilograms times A is equal to T minus W2, which is 225 from up here. So I take the, which one do I do? I think I solved for T from the first equation, plugged it into the second equation, so that I eliminated the T, but now I have A. I have two occurrences of A. So if I subtract 15A from both sides, I'll get negative 38A. And if I add 80 plus a negative 225, I get negative 145. Divide 145 by 38, you get 3.8 meters per second squared. So that's the acceleration. So it's positive 3.8 going up the ramp, and it's negative 3.8 falling down. Then I take this acceleration, plug it into this equation that I had used for the substitution, and I get 137 newtons. I think that was it that I had to do. Okay. Now the final one, I'm shooting this object at an angle of 31 degrees relative to the horizontal. The magnitude is 105 meters per second. That's my initial velocity. So I break it up into the two components. The horizontal side is the x component, so it's the times the cosine of the angle. The opposite side is the vertical component. So you multiply by the sine of 31 degrees. You get these two components. Now, because the y distance is going to limit how far this thing goes, it's going to hit the ground, I use the y direction first. In the y direction, with y positive going up, the acceleration is negative 9.81 meters per second squared. The initial y velocity is going up, so it's positive 54.1 meters per second. Delta y is negative because I'm going from here down to there, so it's negative 100. So I've got three givens. I can use equation 4 to solve for the velocity. Notice I've got negative acceleration, negative delta y. I get plus or minus 69.9 meters per second, but it's falling down to the ground, so it's negative. Then you take that velocity, use the second equation, solve for t. So use this equation, solve for t. You get negative 69.9 minus 54.1 divided by a sub y. You get 12.6 seconds. So that gives you the time it takes for this thing to go up and back down again. You take that time in the x direction equation, which is constant velocity. So it's 90 meters per second to start with, and it's 90 meters per second to end with. So you take 90 times the time, seconds, you get 1,140 meters. So that's how far it goes horizontally. Now, the object is going to be coming down at an angle like this. So it's going to have negative 69.9 meters per second with the y component of velocity. The x component's the same as it was initially, 90. So you got a horizontal component of 90, vertical component of negative 69.9. You have this velocity triangle. The hypotenuse is just this side squared plus this side squared. Take the square root. So you get 114 meters per second for the magnitude of the final velocity. And then opposite over adjacent is tangent. So you use the tangent to find the angle. So you take the inverse tangent of negative 69.9 over 90. You get negative 37.8 degrees. And that is the solution to the problem.